is Tom Daly. This talk is going to be on Anycast routing and how you can use the Anycast routing method to enable local delivery for your applications and data. I'm the Chief Technology Officer at Dyn Inc. We're the guys running around wearing the DNS is sexy shirts. We truly think DNS is sexy. You've used our products before if you've ever used Dyn DNS, and the product that we roll the Anycast network behind is the Dyn platform. So if you're interested in those, see me afterwards. But this is more about how you can use Anycast for your services and products. So quick agenda, what are we going to do, how you set up Anycast, some tips and tricks, and some big drawbacks, caveats of using Anycast. So what is it? It's a packet routing mechanism technique that primarily relies on routing protocols such as BGP and OSPF to deliver homogeneous TCP and UDP services across the network in geographically relevant locations to where your users are by sharing a common IP address amongst your applications. So what does the internet typically look like? You have the internet cloud in the middle, you have some server down in the corner with an IP address that people are going to, and users who are geographically close to that server get a fast, low latency experience. Whereas as you get further and further away from the physical proximity of the server, that latency gets greater and greater and greater because you can only get packets through fiber optic cables so fast, the speed of light kicks in, and users, say, on the West Coast, get a less throughput than those on the East Coast. So what Anycast actually allows you to do is replicate your servers in multiple geographic locations around the world, and as long as you carry the same homogeneous data set across those servers, you can actually serve users in different regions from different servers just by using the same IP address and sharing that IP address over and over and over again. So that's what we're going to talk about. So how can this help you? Well, if you're running dynamic apps that can stand on their own independent from kind of the mothership, if you will, you can CDN-ize your dynamic applications without using some sort of dynamic application front end. Such as a formal CDN that has dynamic app support. So if you went to Arthur Berkman's talk yesterday, he actually does this with Varnish. He just has Anycast Varnish nodes all over the world, proxying back for Wikia. You can do in-datacenter load balancing with this. So if your app doesn't need layer 4 through 7 load balancing, layer 3 is enough, you can do stateless load balancing in your data center with Anycast. You get rid of the locks that you used to have, or software appliance, and you reduce the latency of delivery in your data center with this. It also can allow you to fail over between data centers or perform maintenance without users ever knowing anything's ever gone on because you just withdraw the routes. I'll talk about that in a moment. And then another interesting thing is you can contain denial of service attacks to particular regions of your network. You can have a multi-gigabit DDoS attack hitting the West Coast, and your US Central and East Coast European APAC customers never even know anything happened. So let's talk about how we set up Anycast. A couple different components. The basic concept is that you're going to take your application data and your app itself and make multiple copies of it across the network. Now, if you're going to share data in your app, let's say in our case it's DNS zone files, we just kind of copy them around using standard techniques. XFR, AXFR, rsync, whatever you might want to do. MySQL replication, all those things just work. You have a flat network over multiple data centers like you've always had. We all know how to do this. But then you assign a duplicate IP address or a VIB that's shared to all of the front ends in the data centers. So it doesn't matter where in the world you are, you can hit 208.78.70.1 and you could get routed to totally diverse data centers. And then the secret here, what really makes it Anycast is you start injecting the same route prefix into provider backbones. So I'll take you over how that prefix announcement works in a second. So this is just a diagram of the same thing. You have the orange line representing my data center to data center application and data replication that's going on. But users are, West Coast users on the left are being directed to the server on the left in the west. East Coast users on the right-hand side of the screen are being directed to the application server in the east. Automatically, just happens. So what does it take from a business side? You're going to need some routing guys. You're going to need some app design guys. And your operations staff is really going to have to understand how the network is driving the delivery of the application. So we use an integrated engineering and operations team at Dyn to do that. So in terms of the routing components that you need to know about, basic next-hop static routes are an absolute must. You have to know how they work. You're probably going to want to have a working understanding of how to use Forward Gateway Protocol, BGP. If you're going to do in the data center load balancing, that's when you get into some of the IGP with OSPF ECMP tricks that you can play. And BFP is something we've added in to simplify the whole process. I'll talk more about that later. The other thing that helps is if you have a good working understanding of what internet peering is versus internet transit. So how many of you guys buy, connectivity from an ISP in your data center, right? Does anybody have or buy peering for their networks? Okay, so not too many hands. The difference, when you buy internet transit, you're buying a full routing table. When you plug that link into your servers and you set the default route out at your ISP, you can go anywhere you want. You're paying your ISP to carry you anywhere on the internet you want to go. When you're getting peering from somebody, peering can be paid or settlement free, meaning you don't pay, you're just exchanging traffic between networks. But usually in a peering arrangement, the data that you get, the routes that you get, lead you to that other network or that other network's customers. You're not going to go upstream through that. So you need to really understand and respect the difference between peering and transit when you're going to set up an Anycast network. So basic next-hop routing. This is a route dump from a Juniper router. On the left, you have a prefix, two prefixes. The first one's 1.12.0.0/24. And it says, okay, if I get a packet that I need to send there, how can I get there? And there's 3 different paths. There's 3 BGP paths. The one next to the star is the best path. It's via AS174 to 1239 to 4837. 4808 is a really long path. But that's the best path. That's been computed by BGP as the best path. For those who don't know, AS174 is cogent communications, right? That AS number identifies them, and I'll tell you about that in a sec. The second path is by AS6453, that's top. The third path is via 2914, that's NTT. But the important thing to note here is the next hop IP address and the next hop interface. So generally when you're doing routing for any given prefix that you're going to send packets at, you have a next hop IP, and as a result of having that next hop IP, you resolve a next hop interface. A packet comes into a router, you do a route table lookup, you say, okay, this is going to be my next hop. You do an interface lookup, and you say, okay, now I know what interface I'm going to forward this packet down, shove the packet down the interface. You really have to understand this concept to make Anycast work. So how do you get routed on the internet in general? We'll kind of go with the general terminology first, and then we'll break it down for Anycast. So ISPs use BGP to exchange routing information between their networks. So I'm a Comcast customer at home. Comcast runs BGP with a lot of the other ISPs, almost all the major ISPs on the internet. They're running BGP back with Comcast. The IP addresses that represent my home internet connection get aggregated together from all the people in my neighborhood and broadcast out to the internet as a prefix. That's what a prefix is. It's a collection of routable IP addresses. And that prefix announcement is shared amongst the ISPs. So it's basically like saying, hey, by the way, if you need to get data to me, I'm over here. So if you need to get data to 24.78.80.1, just send it this way, this is me. Now within the ISP's network, ISPs use something called an interior gateway protocol, or an IGP, to route traffic inside the network. It has a lot more data about it. An IGP says, not only can you send data, not only can you get to me by taking this path, but by the way, this path is over here, but the cost to take this path is something. There's a network cost to taking this path. And by having this data, this cost data inside your network, you can determine what links you're going to use and how traffic's going to flow. So that's important to know when you're going to set up Anycast. A group, an ISP that's running an IGP, generally has something called an AS number, an autonomous system number. I was showing you some of those before. 174 is Cogent, 1239 is Sprint, 6453 is Tata, 2914 is NTT. Those are unique identifiers for a network running an IGP. And that's how you generate AS paths. So that's how you say, these are the networks I'm going to traverse to get to a destination in a BGP world. So once you get BGP up and running, you can also use IBGP inside your network as an interior protocol. We won't go over that today. That's usually for the larger network providers, but it's something you can do. I just wanted to reiterate, eBGP only exports the best path between networks. So if I'm on ISP, and I have a couple different routes in my network to get to a destination, when I'm peering with some other ISP, I'm just going to tell them what the best destination is, not all of them. And again, BGP doesn't know anything about link state or topology. So if I'm sitting on my home cable modem, the red guy, on Comcast, and I'm trying to get to some server down in the left, and I transit over a couple ISPs, I might go through 2 of them. I'm buying transit. I got my co-located server that's also buying transit for those respective ISPs, so I have full routing cables. And then the ISPs are peering with each other. And they can peer with each other at a variety of geographic locations through a variety of means. Sometimes it could be, they literally may be in the same co-location facility with a piece of fiber optic cable thrown over the wall at each other and plugged in. Or they could go over something called shared internet exchange infrastructure, which is basically a large layer 2 switch in a data center. But this is how traffic exchanges through networks, through this peering mechanism. In this case, ISP 1 and 2 have 4 different peering links, and I'm using the second peering link. And you may ask yourself, why? Why 2? Why not 3? Why not 4? And that's where interior gateway protocols come into play. So interior gateway protocols such as OSPF or ISIS or even RIP really understand how the internal guts of the network are architected. They know about the network topology and how to move data bits around the network based upon cost of using certain links. ISPs will use this for traffic engineering in their backbone to say, oh, we're really busy in the Northeast, so we're going to push data off and away from the Northeast for whatever reason. Bleed traffic to other links that may have more capacity. One thing to keep in mind in Anycast or with all routing, generally the shortest path or the first path to get you off of the network is the path that wins. Because as an ISP, the longer time I have to carry your bits across the network, the more money I pay to carry those bits. So if I could take your bits and hand them off to somebody fast, I'm making them carry it, and I pay less money. So a lot of people call that the hot potato routing method. So let me dive into the deep details of IGP routing for a second. Pretend I'm an ISP. I have a blue network. I have 6 routers. They're located across the United States. And I have links between those routers. When I set those links up, these could all be 10 gig. They could be 1 gig. They could be 100 gig. They could be 16 by 10 gig, flagged together in a bonding group. I assign costs to these links in my IGP to say how expensive it is to move around the network using these different links. Because presumably I want to carry bits on those links for the shortest amount of time as possible. So when traffic actually routes, what does that look like? Well, the user in the upper right-hand corner, his packets enter R3. And then R3 says, well, I have 3 egress links that leave me. And there's a couple different ways I can get to the server down in the corner. But the cheapest and least cost path for me to go is across that R3 to R4 link with a weight of 20, right? And then for the guy over on the left, who's also on the same ISP, maybe in a totally different side of the country, he's connected to R1. R1 has 2 choices to forward him onto, either R6 or R2. Well, the cost to go to R2 is 50, the cost to go to R6 is 15. So I'm going to forward those packets via the 15 cost link to R6. Once I get to R6, what's my next step? Well, I can go across R70 and that'll move me forward, but I have a 10 cost to R5, so I'm going to forward the packets to R5. And then finally, R5 only has one choice: send the packets over to R4 to the destination server. This is how packet forwarding occurs in a large-scale backbone on the internet. So now this is kind of where we exploit for Anycast. So now let's take this up a scale. This is one ISP forwarding data, right? So what does it look like when you have 2 ISPs that are communicating with each other? So now I have that same blue network, R1 through 6, with another ISP. It's a little bit smaller. They only have 4 routers, RA, RB, RC, RD. And they have a totally separate backbone. But they also have peering links between the red network and the blue network. Those are those orange lines up there. So R1 has peering to RA, R3 has peering to RD, R6 has peering to RC, R4 has peering to RD. Right? So 2 different networks peering with each other in 4 geographically diverse locations. When you guys hear things like the May East or the May West, or the YAMSIX or the PAX or the Equinix, these are those locations where this internet peering is taking place, particularly in the United States. So, how do packets route across those networks? Well, if I'm sitting at my house, again on the blue network, I'm a subscriber to the blue ISP, and I'm directly connected to R3, and I'm trying to get to a web server hanging off of the red network's RC router, I have to traverse those 2 ISPs. So what is the packet flow here? I come into R3. R3 says to me, well, I have internal connections that can get you other places, IBGP or IGP connections. But it also says, hey, I have a peering link out to the red network router RB. And we said earlier, hot potato routing always wins. So this is an opportunity for the blue ISP, which I'm connected to dump that traffic to some other provider as quickly as possible. That's good for them, right? Because they don't have to carry their bits around that backbone anymore. So they dump the traffic immediately to RB on the red backbone, and now we get into the red backbone's IGP, and they say, okay, what's the best path to forward packets on from RB to get towards that server? The cheapest link cost, and it's not drawn on here like it was before, is to RD to RC and then to the server. This is just how basic BGP, IGP, and IBGP routing works on the internet over and over again. So now we can get into like how we exploit this to make Anycast work. So Anycast, getting to the data center. You're going to use this routing to basically attract traffic to a data center based upon the prefix and how far that prefix pushes out into the backbone, or how far it's propagated out into the backbone. As I said, it relies on your transit and the routing policy of your ISPs that you're buying transit from to sanely get packets to the right location for you, unless you're going to set up your own large-scale backbone, which I don't recommend doing because you'll probably run out of money and go out of business, so don't do that. And sorry for the typo there, but you can also try and do this with peering, and a lot of Anycast networks are heavily peered. I would just, as beginners, shy away from that. It's going to add much more complexity and potential for latency than is really worth it. So if you're going to try doing this, just start doing this on your transit links to get started. So let's take that one single blue ISP again, right? And we'll put a user on the West Coast and a user on the East Coast and a server on the West Coast and a server on the East Coast, and they're both sharing the same IP address. Well, how does the IGP in the backbone carry this traffic? It says, okay, for the West Coast user who's directly connected to R1, what's the cheapest way to get off of that router? Link cost of 15 over to R6 and dump me to the server that I'm trying to get the traffic off of, or the content off of. Same thing for the East Coast. I'm a single home subscriber on R3, and I want to get to the server. Well, what do? Take the link down with a cost of 20 to R4 and get to the server. Now, the clients don't know anything has happened here. They've just initiated a UDP connection, like a DNS lookup, or an HTTP query to this IP address. And because the ISP is consistently routing this traffic in their backbone, it's just going to whatever server is nearby. And say I'm just running a very static website there, like, Hi from Dyn is the homepage there. There's nothing that's going to break based upon session. It's just an HTTP session that goes that way for one guy and goes that way for the other guy. But what we've done is we've reduced the latency for the West Coast user who was originally trying to get to the East Coast server from 80 milliseconds down to 10 or 20 milliseconds. And what that does for your overall effective TCP throughput is it absolutely maximizes it. Because latency is the killer for TCP throughput. This is how a lot of CDNs work, and this is where you can actually roll your own. If I'm running a dynamic web application, well, if I can sync my state on the backbone fast enough and move data around, or I just decide to run my application stateless, just like a lot of our other presenters have been talking about, you don't need consistency, then this works. You've sped up your website phenomenally, or your application as a result of this. So now what does this look like when multiple backbones are involved? Well, here again, I got my servers hanging off the red network, same IP addresses being injected into the red network. I got users on the West Coast and the East Coast. Same thing. So the user on the West Coast enters the network on R1. R1 says, I want to dump this traffic. It's not ultimately destined to my network. Dump that off on a peering link as quickly as possible to the red network. The red network's IGP kicks in, carries the traffic to RC, and hands it to the server in the lower left-hand corner. West Coast server. Same thing on the right-hand side of the picture. So from your application perspective, if you're running something that's UDP-based, say you're going to Anycast DNS or Anycast NTP, Network Time Protocol, this works great. It works incredibly well because it's, generally speaking, one packet in and one packet out. So you don't have to worry about session split brain issues if the network topology were to change underneath you during a long-lived TCP session. For TCP, if you're running a modern website, chances are your TCP connections for that website are incredibly short-lived. Go get a piece of CSS. Go get a piece of JavaScript. Go get some images. Go grab the HTML. We're all trying to build faster and faster websites. So what's the session time? 500 milliseconds, 600 milliseconds, actual TCP session time? It just works. It's a short-lived session. And a lot of people have said, well, Anycast doesn't work for TCP. Anybody use Dalnet IRC? IRC is TCP-based. IRC.Dalnet has been Anycast for the past 6 years. No problem. The network topology changes are not occurring fast enough that it breaks session against multiple servers at the same time. If you're doing something like downloads, some sort of download or stream or video, this might not be the right thing for you, but there are some techniques around it by using things like short-lived HTTP redirects, and we can talk about that afterwards if you're interested, if that applies to you.
I have a question on the short versus long-lived.
Sure.
So most of my connections with HTTP use 1.1 with keep alive for about 900 seconds.
Yep.
Is that short or long?
That's short. That's short. Now, the other thing you have to weigh up your app design is if the user should end up at a different data center in that 900-second window, and that keep alive ultimately expires, if the session lands on another data center that says, I don't have state for you, reset, does your app entirely break? If it's, depending upon what your app does, and it just gracefully says, oh, I just go restart my session and then renegotiate, then you're fine. If it had some sort of open stream there that was critical or time-bound, you could run into a problem. So in terms of designing the app, very important that your data sharing or your replication happens across regular unicast addresses. So if your developers don't know, hey, when I'm going to bind to a socket to actually talk out for this app, I need to bind to a unicast IP on an interface versus the anycast IP. It's something you need to build into your app. The VIPs and the frontends are anycasted. We were just talking about this. TCP state is generally reset or completely ignored if there's a topology change in the network. And there's a couple ways around that, which is that your application session data really can be just reset when routing changes occur, or you need to make sure that that app session data is completely shared. And that's just not something like a cookie or a time zone setting between multiple data centers. This gets to, you need to share the state off your front-end load balancers, that this is a TCP connection in state, TCP wait that's established between your load balancers, between your data centers. And it can be done, it's just whether or not your data is long-lived enough to replicate that state around your network. And then operations components. Your application's availability monitoring suddenly will scale much differently than you've ever been used to, because no one monitoring location, no one external monitoring location can monitor your entire network, right? Because they're essentially blind from other pieces of the network. If I have a West Coast and an East Coast Anycast, and I put my monitoring box in the West Coast, chances are it's only getting routed to the West Coast Anycast node. And that East Coast node is now going completely unmonitored, which is a very bad situation. So you need to be able to set up enough monitoring to cover all your Anycast installations. For reference, at Dyn Inc, we have 14 POPs. We have something like 22 installations of Nagios running around the network.
Could you also use both an Anycast BIP and non-Anycast BIP?
Absolutely. Yep. Yep. So trend and load monitoring becomes really important. because you might want to take an entire facility down, or you might have a localized Anycast outage to a facility. And it's fine that your traffic in that facility went down. You should see corresponding facilities pick the traffic rate back up, because the network's going to converge underneath the application and send lookouts or queries or whatever it might be, transactions, to different places on the network. So your trend monitor, you should see a nice flat line, or whatever your diagonal pattern is, but you're going to see traffic shift between nodes. And suddenly your team, everybody on your team needs to know a lot more about networking than they used to. The network's not really for granted anymore, so they need to know about things like BGP, OSPF, etc. So another question?
When you, for example, if you want to take a facility offline, is there any benefit to changing the cost of a route to slowly drain away traffic, or I guess you're breaking your TCP stuff anyway, so or do you just shut it off?
Yeah, because TCP, so the question was, if you're going to perform maintenance on a node, you try and bleed traffic off. And you can't really do that because that TCP session state is hanging there, and you kind of just got to cut it off and move your clients to another node. I have some diagrams of that. So, just talked about availability monitoring as well. I'll point out like a remote plugin executor, like NRPE2 for Nagios, really helps with this, because you can still monitor all these Anycast VIP heads at different data centers by getting your check originating from within that data center. So trend monitoring picture of that. This is what one of our DNS network graphs look like. So these are all the servers on the right here. I'll contribute to this, weekly trend graph. So if I do maintenance on a node, say the bottommost orange node, I'll see all that traffic, drop off that map or off that chart altogether. I shouldn't see the top line change at all because the traffic should reconvert onto other sites. So some other site's going to get fatter, or a couple other sites are going to get fatter. Question in the back?
Can you go back to one slide?
Yeah.
So when you're suggesting that you monitor Anycast within data centers, does that mean that there is no inter-DC traffic for the Anycast IPs?
Right. Yeah, you don't want to have inter-DC Anycast traffic, because there's a couple problems with that, but one of them is if you made a real bad mistake, you've actually Anycasted your source IP as well, and now you have like diverging return paths, and you'll actually never get the packets back. So you want to source from a unicast monitoring point to an Anycast endpoint that your routing policy contains to the data center. Does that answer the question?
I was just asking for clarification.
Okay, got it. So let's talk about some tips. So kind of gone over like how you set it up in some kind of like high-level detail. You have some IP addresses. You route them from multiple data centers on the same paths. You rely on your provider's IGP to split traffic to your data centers for you. But now I have some tips and tricks. So the first one is selecting an ISP that you're going to go with for Anycast. If you're going to start Anycasting, you actually should use the same ISP at every location you're going to run Anycast from, because that's how you take advantage of that IGP traffic splitting that I showed off earlier. So you need to be using the same ISP. If you want to use multiple ISPs, you need to have enough of a saturation of ISPs that you're not going to cause regional problems. And I'll show an example of that with Tokyo in a moment. The ISP itself needs to have coherent routing policy inside. If they don't have their IGP tuned correctly, you can start sending traffic all over the network, and your monitoring is going to have to pick that up, and you're going to have to call their NOC and say, hey, why are you taking traffic that's on the West Coast and dumping it into the US Central region? That's something we have our monitoring systems doing all the time. Question?
So a lot of people here buy transit from multiple providers for redundancy reasons.
Yep.
Isn't that break what you just said?
It will break it, yes. Yep, you need to be buying, you cannot be buying like blended bandwidth as you can buy at a lot of co-location facilities. You need to go out to NTT, AT&T, Verizon, these larger backbone providers that have coherent routing policies within their backbones to get reinforced Anycast paths. Yep.
I guess my question was, say you do this on Cogent.
Yep.
There's a provider.
Yep.
And they'll keep yours Cogent.
Yep. Well, that's going to happen to your unicast traffic too.
Well, that's why I'm saying people buy two, they buy from Cogent and level 3.
Yeah, and you can anycast on both of them. Just have Cogent and level 3 at both of your locations. Yeah, it is costly to do this. But if you want app performance, it gives you a ton of app performance. One thing that you can suss out a provider who's going to be a good Anycast provider is find out if they run a single autonomous system number for their entire network. If they run one global ASN, it's a good hint that they have a coherent routing policy across their POPs. The other thing you want to check is their interconnect policy. So if you're connected to a provider who has a I'll peer with anyone, anywhere, at any time type peering policy, you can run into issues, right? Because what happens if they peer with some guy like on the West Coast only, and he has East Coast eyeballs? Well, those East Coast eyeballs are going to run across his backbone to the West Coast peering point, and then land in your West Coast Anycast node, when they should have just gone over transit to your East Coast Anycast node. I have some pictures of that too. In terms of IP addresses, you're going to need your own IP addresses, you're going to need to be able to speak BGP, you're going to need your own ASN. Go talk to ARN for that. You're generally going to Anycast with a /24 block. You probably don't have a reason to use more IP addresses than that. And one tip is to nail down the /22 route in BGP, so announce the /22 route from one of your data centers out of the Anycast cloud. So that way if you have some sort of route flap issue, you don't black hole all your traffic. So look it up, it's called route flap dampening. It's where too many BGP transitions occur in a period of time. Some routers will just take that flapped prefix and say, I'm ignoring it altogether. But if you have a 22 holding over the 24, you're going to at least get that traffic in one data center. And you hope to God you have enough capacity in that data center to service the traffic coming at you. Otherwise, you just DDoS yourself. Third tip, no backbone. You really do not need a backbone to run Anycast. There's a lot of people who think you need a backbone to run Anycast. You don't. You can use one or two ISPs, as many ISPs you want, as long as they're coherently and homogeneously connected. Something that you will need to do is allow your own ASN to be heard back into your routers. So normally routers say, if I hear a route from my own ASN, somebody's trying to do something bad here. But think about it, if you have data centers that have no backbone between them sending data to each other on the unicast IP blocks, they're going to come from the same ASN. So you need to allow that route to get back into your router. So on Juniper's, you're going to say, routing options autonomous system 33517 loops 2. That says I can have 2 instances of my ASN number inside the routing update. On Cisco, when you configure the neighbor statement, neighbor black allow AS in is what you need to use there. So a couple tricks. Let's talk about outages and maintenance. Anycast allows you to route around outages and maintenance in a very elegant way in a somewhat automated fashion. So in an Anycast cloud, if your site breaks, if one site out of 2 or one site out of 10 breaks, just withdraw your routes. All of a sudden, your upstream ISPs, all your peers will say, well, that path isn't valid anymore. I'm going to invalidate that path, and I'm going to find the next best possible path. Make sure you don't flap your route. So if you're going to do maintenance and you're going to pull down a data center for some period of time, take it down, leave it down for half an hour, and then re-inject it back into BGP. Don't sit there going, I pulled it out, all right, I put it back in, oh, I forgot to do something, I'm going to pull it out again, now I'm going to put it back in. You just caused flappage in BGP. Chances are you're getting route flap damage. The other thing is before you fully recover and re-inject your routes, you need to resync all your application data ahead of time before you put production traffic back. So, picture diagram of what that looks like. So, normal Anycast setup, everything's happy. I take that lower right-hand node out for maintenance. RD just says, oh, I don't have a valid next hop out to that server anymore. What's my next best path? I'll send it off to RC over to the destination. So that could have been a controlled outage where I actually withdrew the routes from that server going to my provider, or something actually went bad, BGP went down, and I automatically routed around the issue. We do rolling software upgrades through our network this way. We basically start at one side of the world, tear the site out of Anycast, let traffic go to other data centers, roll the code upgrade, re-inject the path, take traffic back. Is everything okay? Yes? Move on to the next data center. We can do this following the nighttime. Most people say follow the sun. We follow the night when we're doing rolling code upgrades across the network. So another trick, which is Anycast in the data center I mentioned. So who's running like some load balancers in their network? Pretty expensive, right? Do you know if you really need them? If you're only looking to spray packets across multiple front-end servers, you don't need the load balancer. You can do this with Anycast. So since you're inside your network, you can use an IGP, an interior gateway protocol, and you can use a phenomenon in routers called ECMP, equal cost multipath routing. Anybody remember the days where you could get 2 T1s from your service provider? And you had the main T1 and then you had the shadow T1? Or you had 2 T1s and you were like, rock on, I got 3 megs, 1.5 by 2. They do this with ECMP where they're just load balancing packets across equal cost paths. The 2 T1s are equal cost paths for those routers, so they load balance the packets amongst them. So what does that look like? Well, I got my router facing out towards the internet with the Anycast prefix I'm announcing. I have 2 servers with real unicast IPs on there for data replication purposes and management. That's what I SSH it to. But then my VIP, in my case it's DNS, but in yours it might be DNS, is assigned to loopback on the box. And then I'm using OSPF to inject that into an OSPF area that the router participates in. So then the router says, hey, if I go to 208.168.70.1, what is my path to that? And it says, well, you actually have 2, and they're equally balanced. So I'm just going to load balance across those paths. You just got a load balancer for free, and you experience no latency in your network by having an additional piece of hardware. So you can do this if you have a Juniper router or Quagga box, out in front, and you have your application servers behind that. Throw Quagga on them. Configure Quagga to take the loopback interface and inject it into an OSPF area that your router participates in. The router's going to say, okay, I see valid next hops. Most routers, by default, will not load share across those next hops, so you have to enable that. So I'll show you how to do that in a sec. But then the router basically starts hashing across the 2-tuple source IP, nest IP, or the 4-tuple source IP, source port, nest IP, nest port, and that's configurable up to you. That's something you need to figure out if your what your application can support. Now, one thing to think about when you're testing this in the lab is if you're using this type of flow hashing, you can run into kind of a scenario you don't expect in the lab where you say, all right, I'm hitting my VIP, and it's only hitting one box. It's because it's not true round-robin load balancing. A traditional load balancer will say, okay, first packet goes here, second request goes here, third request goes here, fourth request goes here. This is a hash tuple. So if you're always coming from the same source IP, chances are you will always get hashed to the same front-end server. If you come from a different source IP, you might get to the other server. So you have to test that in your lab to understand what's happening there. And then the nice thing is, if something happens with an individual box in the data center, how do you deal with that? Well, you just cause a routing convergence. Take the OSPF neighbor down. The front-end router says, I don't have paths to go there anymore, and just chooses another path. Question?
If you have like 4 boxes and one goes down to 3, does that break all the sessions on the other hashes? Or
yes. Yeah. Because those other boxes have no concept of the TCP state from the box that went down.
Right.
Now, you could get super serious and replicate that state yourself. I've seen people doing that.
But either TCP sessions would need to be reset.
The TCP sessions would need to be reset. Yeah. So here's the config for doing that on a Juniper. You say when you're forwarding routes to the forwarding table, load balance them by a clause called load balance, and then you just say when you're evaluating routes to export to the forwarding table, if they match this prefix, load balance them per packet, and then I configure what type of load balancing I want. Layer, the 2-tuple or the 4-tuple. I have other configs. If people are interested, I can send them out afterwards. So trick number 3, partitioning and DDoS. So the nice thing about Anycast is that sources generally consistently hash to the same destination server. And the DDoSes, at least that I see, should tend to generate reasonably from one region of the world. Or from a couple different regions, but not everywhere, not fully distributed perfect storm all the time. So since that's always mapping to one, a set of users in a certain population map ultimately to one endpoint, you partition your DDoS. So here's my 3 user populations hitting my 3 sites of Anycast, everything's fine, and suddenly some users on the West Coast come along and start DOSing me. Well, they only map to one data center. So that data center gets taken out, but somebody in the central and the east region never even knew anything went wrong. So I can, try and stand up my mitigation tactics on the West Coast, or I've just had a single regionalized outage versus a complete global outage. Couple caveats to go over. So one of the things that burned us at Dyn was some poor network planning. So we were turning up a POP in Tokyo with one of our provider strands, and for most of our network, we were using level 3 in the United States and Europe. Level 3 doesn't have a backbone in Asia Pac. So we went to another provider, PCCW in Asia Pac, and said, hey, we'd like to get a connection from you, and we'd like to anycast over it. Now, PCCW actually has a global backbone. They have network presence in the US, Europe, and APAC. So when we turned up our routes on PCCW in Tokyo, we didn't set what's called the BGP community on them to say that these routes should be contained to the APAC region. So those routes actually flooded across PCCW's backbone, and those people who preferred PCCW as a peer sent all their traffic down that path to PCCW, and all that traffic got carried across PCCW's IGP to our single site in Tokyo. So if you were sitting in Paris, and you're trying to get to this IP address to do a DNS lookup, you're probably pretty disappointed that your packet crossed, the transatlantic fiber system across the United States, across the Pacific, and then landed in our Tokyo data center. So I'll show you what that looks like. This is what we planned. We said, we're going to have Europe users transit across PCCW to level 3 and get to our servers in Europe. People in the US come across PCCW, get to level 3, go to our server in the US, and then PCCW users, or any user in APAC, across PCCW, come across the orange PCCW box, which is that local network, into our server down there. When we screwed this up, because we didn't apply the right community tag to suppress routes from leaving the Asia-Pac region, what actually happened, it looked like this. Basically, everybody said, oh, well, the blue and the orange are the preferred peering path that I'd like to use between these 2 networks. I don't want to pay for transit until level 3. Just sent it that way, everything landed in Tokyo. So we went from 20 millisecond service times on that VIP globally to 20 mils in Tokyo and 175 to 120 in Europe. So we got burned pretty badly on that. So you have to be able to test your Anycast nodes significantly. So we now have a prefix of IP addresses, a block of IPs in our network reserved solely for testing. We stand them up to test, our routing policy and how we move packets around our backbone and our provider's backbone that customer traffic never ever touches. The nice thing is when it's time to turn that into production, we go into our configuration management system, strip out those IPs, put the production IPs in, and push. You're all set to go. This can also be really useful for DDoS testing. So if you want to know how well your app's going to hold up to a DOS, go grab some Amazon nodes, write some shell scripts, have them come hammer this test prefix with something like Apache Bench or your own custom written UDP hammer. Not that those exist, but you can get them. It's also a great way to do engineering and operations tabletop exercises. You can talk about how routes propagate and play with your routing policy without impacting your live customer traffic. You just think of those prefixes totally isolated from one another. So remember how I said we do ECMP in the data center for load balancing without a load balancer, and we were using OSPF to do that? We thought this worked really well until we decided that Quagga running on 16 servers to achieve ECMP was too heavy. Because every time a server would go down, 15 other nodes would need to realize and recognize that topology change, and that was pretty heavyweight. So the router at the end of this network would sit there and say, everything's fine, one box went down, OSPF starts recalculating topology, and the CPU usage on the router would spike. And it made us nervous, so we said we're not going to do that anymore. So what we really need to do here was have a new way to enumerate next available hops for equal cost path next hops. So we came up with BFD. So OpenBFD is an implementation of the BFD protocol in PreviousD. BFD is normally used for Ethernet operation and administrative information in metro Ethernet networks. So think about like an old school T1 line. If a T1 goes down on either side of the circuit, the telecom provider knows how to signal that loss of link alarm down the line. So you unplug the T1 in New York City from the jack on the router, and the guy sitting in Los Angeles at the other end of the T1 loses link. Like they get a link loss alarm. In Ethernet, that doesn't happen, especially in metro Ethernet, because you might have, your router, a switch, another switch, another switch, another switch, another switch, and then the other guy's router. Well, if one of those intermittent links go down, there's nothing in Ethernet that says forward the link loss out either side. So the only way your routing protocols know to reconverge is for a hello timer to basically expire, which usually in like BGP or OSPF is about 3 minutes. So now you're blackballing traffic on the floor for 3 minutes. So BFD is a shim that verifies forwarding plane capability across a shared network to make sure that you can actually forward packets, and will tear routing protocols down in under a second if they can't forward packets across that forwarding plane. So he said, well, why don't we use this? We can use this to enumerate next hops. So we wrote OpenBFD. Our Juniper router has already supported BFD. And so now what we do is we form a BFD adjacency between the router and the DNS server. We use just basic static routes configuration in our router, but rather than saying route 208.168.70.0/26 next hop this IP address, we tell the router that it's a qualified next hop. And what that means is that there needs to be an active BFD session with a neighbor before you'll send traffic to that neighbor and enumerate that static next hop as being available. So this gives us sub 1 second reconvergence times for handling local box failures in the data center. So how does this work? Well, we have data tools run BFD beacon. BFD beacon comes up, it forms an adjacency to the router. The router says, cool, I have a next hop available to me. I'll start load balancing traffic to that next hop. And then we have a separate monitoring process that's checking, bind or unbound or Apache or whatever our service delivery engine is. And if it detects a problem with that service delivery engine, it just runs SVC minus the BFD beacon and tears the BFD beacon down. The router goes, hey, I can't forward packets there anymore. These little check packets I'm forwarding. So I'm going to tear the next hop down. Traffic leaves that box. Things move on. One thing you do have to be careful of is if you don't nail down your routes in your router appropriately, and all of your component routes disappear from the aggregate, the /24, that you're announcing out to the internet, you may inadvertently withdraw your 24 as well and cause flapping. So a lot of times we'll nail down a 32 on the router and prevent that from happening. So that way we can control when our routes are pulled from the internet or re-announced into the internet. But you get, you now get a health checking mechanism that can figure out if something is down and reroute traffic in less than a second. So we've actually decided to open source this code. It's available on GitHub. That's the URL. If you guys are interested, go check out the source and try it out. We'll make sure this presentation gets posted so you have the Juniper configs as well. And that's it. Hopefully I didn't run through that too quickly. You can take questions for a couple minutes. Yeah?
So when you're running anycasted DNS servers, frequent use cases to load balance to CDN nodes that are close to you, which might not be anycast. Does your DNS product also consult the BGP tables to know what non-anycast IP addresses to hand out for
For Dyn Inc, specifically for Dyn Inc, you as the customer come in and say, for the Anycast US region, respond with this unicast service ID in DNS request.
aspect. It's not, you say, I want, here's the list of my web servers on the West Coast, here's the North and East Coast.
You say exactly that. Yeah, you say, here's the list of the web servers for the West, here's the list of the web servers for the East, here's the list of the web servers for APAC, let's say. And then what Anycast is doing is it's basically receiving an attraction to that user into one of our data centers. That data center knows it's in the West, so it says, okay, I'm just going to serve back the West Coast response set.
How do you evaluate ISPs?
So the question was, how do you evaluate ISPs? When you're starting out, you really want to make sure that, for Anycast, you want to make sure that they have a single ASN that's routed globally, they have a homogeneous routing policy. You find out about how their IGPs are tuned. So when we call up an ISP and we want to connect to them, we try and talk to their network architect and understand how they route traffic across their backbone and what their backbone links look like, and make sure that their metric cost and their path tuning between cities actually makes sense. Because if it doesn't make sense, then it doesn't work for doing reasonable geolocated Anycast anymore. SLA is very important. If they can't guarantee you 5 lines, you really shouldn't use them. Because at this point, that everybody can offer 5 lines. It's a trust thing, just like anything else in the infrastructure as a service play. You have to trust the people you're going to do business with. Yeah.
Once deployed, does it require to build more maintenance overhead than unicast?
So the question was, once it's deployed, does it require any more maintenance overhead than unicast? The answer is yes, because you're now managing and performing maintenance on that piece of data or that web service or whatever service you're exposing, however many Anycast pops you have. So you used to be able to say, oh, I'm just going to go, upgrade the operating system on the web servers. Well, now I'm going to go upgrade the operating system on the web servers in 4 or 5 locations, depending on how many locations you deploy. The benefit of that, though, is that you have essentially automatic high availability if you architected your system correctly. Because now you just say, oh, I'm going to go upgrade the web servers on the West Coast. Drop that out of Anycast. No live production traffic is hitting that node anymore. It's all gone off to your other nodes. You can upgrade everything there, test it, make sure it's good to go, bring the site back into Anycast, and move on down the line.
What are the advantages of using Anycast versus DNS or wireless power?
Sure. So one of the drawbacks of using a Anycast DNS that does mapping to unicast is that, generally speaking, the mapping that occurs is based upon the user's recursive resolver, their ISP's DNS server, and not necessarily the user themselves, right? So it generally doesn't come into play, but if you're running something that's highly granular, like you're a regionalized network, and you want to partition, say, users from upstate New York different than users from, the New York metro area, you don't get that level of granularity just by running Anycast DNS and then doing geomapping with Anycast DNS. But if you Anycast within the region, and you Anycast, say, your web services, your TCP services, that connection that comes into you is the original, user's computer rather than the user's recursive DNS server. So you could argue it's more accurate. I think there was a question here. Yeah, absolutely. Treat it the same way. Nothing different. Go get your V6 blocks, layer them on top of your V4 blocks. If you really want to do it quick, get enough. You're always going to get enough V6 space where you can partition the space, and you just say, all right, here's my prefix, so lots of zeros, and then encode my V4 space into my V6 space, and you get the same IP addresses. Way in back.
How would you reconcile the problem of a data center that has really attractive routing, but on a quarter the capacity of and your other data centers?
Get more capacity. So the question was, how do you reconcile the issue of a data center that has really great routing, but not enough capacity to handle the routes that are coming into that data center, or the user base that's coming into that data center? My smart ass remark was get more capacity. And actually, in an Anycast setup, you really don't have a choice other than to get more capacity. There's no mechanism that really allows you to shed load for a subpopulation of users. You're relying on natural BGP routing. So,
but if you're like in an all Cisco network and it's a very large network and you're using IBGP internally, can't you is there any sort of wait mechanism in BGP?
You could certainly tune the IGP metrics to do so. But my assumption in my mind was that you're, a web service provider, and you're not going to have an IGP that you can control. You're relying on your ISPs, and I guarantee you, your ISP is not going to tune their metrics for your situation because it would impact traffic for all of their customers. So you really, if you control the IGP, absolutely, you can move traffic around that way.
You missed the letter. IBGP.
Well, an IGP or IBGP?
IBGP, and for the sake of argument, let's say I am the provider.
Yeah, you can do that. IBGP is an IGP. More.
Follow up on that topic. If you're planning, how do you know? Is there any way to know ahead of time that you're going to end up in that situation where maybe transit's really expensive there, but the routing's really good? Is there any way to know that ahead of time?
Lots and lots of looking glasses, traceroute.org, and Excel. Test it yourself. All right, I think I'm out of time. Thank you very much.